Hello everyone, welcome to the class Applied and Energy Geophysics. This is lecture number 1. In this lecture, we'll talk about signals and systems and engineering problems, and with some examples of them. And briefly, we'll also talk about signal processing and inverse problems. Signal is the variation of one parameter with respect to one or more independent variable, time and spatial variation. So the example is you can listen, right? You can touch and see. And temperature also is a signal because it varies with time. And when you think about the topography, how the morphology of the surface, when you think about the mountain, the elevation changes with the coordinate, x and y coordinates. So that could be another signal. And variation, the earthquake motion can be a signal. So it could be a displacement with time and velocity with time and acceleration with time. And X-ray signal or the images that projected your body could be the signal too. When you obtain the data from one location, it can be considered as the one-dimensional signal. So if you think about the TDL system that's fixed at the one position, and if you collect the reflective wave, and it will show some amplitude variation with time, and this will be the one-dimensional signal because it contains the data, it shows the data of one location. So especially in space, it's a 1D. Here, another example is you have elastic wave source. So it's like a dropping a ball, and you have an accelerometer here and the other one. And in between, you have a hole, so you can see how the wave propagates through the hole, propagate in the soil media that has the hole. So as you pour the water, you can see the changes in arrival time. So accelerometer records the one signal here, and the accelerometer 2 also records another signal. And these signal records the wave at one location, arriving at one location. And what about the 2D signal? So 2D signal will be the one with the variation along the one axis, right? So if you have a ground surface with the water saturation, and you're towing GPR machine this direction, and let's say this is the x-axis, and along this x-axis you're acquiring the signal over some distance, and it will give you this kind of an image as a 2D signal. So each signal here at one location is superposed, overlapped in space-wise, and this becomes an image, what we call the 2D signal. So 1D signal is the one like this. Let me open again. Probably I should share it again. So this is the 2D signal. And what about the 3D? 3D signal contains the data about the elevation, XY, and time maybe. Or it could be XYZ in space. So the other one is system. System is very important. Engineering system transform an input signal into output signal. And the other example is, so you have a input signal. And system transform this input signal to output signal. So then in multiplication of it, if it is a matrix, then it becomes the convolution. So the result y will be h times y, x. And this is called a convolution. We're going to talk about this one very soon, in a minute. Example will be, let's say that you have an Indian Ocean, and this is the system, and earthquake is the input. So you have earthquake having the magnitude of 9.0, then it meets the ocean, then it generates a tsunami. So this will be the result. Right? What about this system? So you have building as a system, and wind is an input. Then, as a result, you will get the oscillation. That's the output signal, output response. Mechanical, and transducer that we use all the time can be considered as a one system. So accelerometer, for example, it transforms the mechanical waves or mechanical vibration into electrical signal or the electrical voltage change. So as you apply the acceleration, it gives you the high voltage or the low voltage, depending on the magnitude of the acceleration. So mechanical input is an input to the transducer, and then the output will be the electrical signal. And pore pressure transducer is the same. You have a membrane that can feel the pressure change, and this pressure is a mechanical input, and membrane changes with the strain gauge inside maybe. It changes the mechanical force to the electrical force. Band element will be the same, and strain gauge, load state, etc., etc. What about the speaker that you use to listen to music, right? The digital music source is kind of it's the record of the electromagnetic signal or the electrical signal, right? And the speaker transforms this electrical signal to the mechanical waves. So it vibrates inside the speaker. That there are some elements that vibrate with this electrical signal. Then it produces sounds. And what about the dam? Dam will be one system, and if there's an earthquake as an input, then this water level will oscillate as an output, or this dam can move and vibrate. So displacement could be also the one of the output. We can look at this landslide from a system perspective. This landslide occurred in 1995 in Southern California, La Conchita, and the cause of this landslide was extreme rainfall. So rainfall could be the input, and system will be this geology, right? And and the output will be this landslide. So in the forward simulation, from cause to effect, it's called the forward simulation or forward modeling. This bottle can be considered as a system, and so it has a system has some shape, right? And then you have a hole at the bottom, and if you pour the water, and there was a valve in the beginning, and then you open the valve, and this water will drain, right? And the flow rate coming out from this hole can be an output signal. And this Q will change with the height and the diameter of this, the flask. Right? So then if you know the shape and you know the input with the water level change, then you can calculate the Q. Q will be the output. So in this case, it will be a forward signal because you know the input and you know the system, so the output that you're curious about is unknown. Huh? But what about the other way? Huh? Now you have recorded the flow rate here, and we know the input, maybe the water level change, but we don't know how the bottle shapes. So then we can inversely estimate the shape of the bottle using this output and input. Right? This is called the inverse problem. Or the other problem will be we know the shape of the shape of the bottle, and we know the output that's been recorded. So then what will be the input? So the water level change maybe. So from effect back to cause, it's called the inverse modeling. And from cause to effect, it's called the forward modeling. So then if we go back to this landslide problem, if we know the heavy rainfall, like how much the rain is gonna pour, and we know the system, so the slope of the this mountain and the geology and bedrock depth or the strength of the soil, etc., that's gonna be the system. And then what will be the effect? Effect will be occurrence of the landslide, whether the landslide will occur or not, or then how far they're gonna run out. That will be the output. Or in the inverse modeling, we can think oppositely, right? We know the result, that landslide happened. So we know the runout distance, and we know that that's happened there. And we don't know the heavy rainfall, then we can inversely estimate how much rainfall was there to cause this much of the landslide. So then in engineering problems, in many engineering problems, we can think the problem and simplify as a input and system and output. Here's a pointer. And in forward problem, if we know the system and we know the input, then we can estimate the output. We can predict the output. So by iterating the system design, we can design safe system. It's called a system design. System is designed to satisfy performance criteria. And convolution is when we know the input and system. So then from there we can predict the output response. It's called a convolution problem. And the other one is the inverse problem. If we know the input and we measure the output response, then what will be the system? Right? We can characterize the system, and it's called a system identification. And last one is we know the system, how the system react to a certain response, and then we measure the output. So then what was the input? That will be the question for the deconvolution in inverse problem. So engineering design, one example of them will be we have a dam building to design, then we have to design, and we can expect the design load, right? So for example, like if it's earthquake, then earthquake comes back in 100 years, magnitude of 7.0. That will be the design load. And dam building that we want to be design, that's going to be the system. And here the design criteria will be if it's like dam, then it should not be cracked or it should not be slide. So that's the design criteria. So we can iterate the system design to satisfy the criteria. And convolution is like circuit numerical simulation. You have a FEM code, and that's built based on the Hooke's law, maybe, or the elasticity. Then system is elastic material, and X is the force, and Y will be the displacement or the deformation. And system identification is a non-destructive testing. So you have input like hammering down the pile, and you measure the obtain the response using the accelerometer, the vibration. Vibration is the result or the output. So then what's the shape of the pile, or maybe the length of the pile, such, etc., etc. Or tomographic imaging. So you have a body, and they have all kinds of source around it, and they receive the source that's propagating and the transmitting through your body, and from that they can identify what's in your body. Deconvolution. So we have earthquake record, that's Y output, and seismogram is the system, and then we can estimate the magnitude of the earthquake. That's going to be input. Or we have a record, and maybe the ground is the system. Then from the three locations, we can identify where the origin, the location of the earthquake source. Or deconvolution, another example is the determining of the source of a pollutant. So you measure the concentration at several locations, and you know how fast it diffuses. So then you can identify the location of the source of the pollutant. So in the class, we can share some examples of engineering problems on your own. So we're gonna do this exercise in the class. System design problem, convolution problem, and system identification and deconvolution problem. Some examples of signals and systems: time and spatial variation in one dimension. It could be acoustic, electrical signals, like signal emitted by a transmission antenna, chemistry, finance, medicine. There are all kinds of signals that we can think of. Geography is a two-dimensional spatial variation. Mechanics, maybe surface roughness. Well, that's how the roughness over X and Y and Z. Right? And 3D volumetric variation is porous network in particulate medium, and fluid mechanics, and CO2 distribution in a bioreactor. That's the when you think in X and Y and Z, then that's in 3D signals. It could be also the 4D signal if you include the time variation. And also we can identify or classify the system into two categories: active system and passive system. Active system uses active sources like bat and dolphin. They cry and howl, right? They speak for their own language. Yeah? And in the civil engineering, when we do the site investigation using a geophone and sonar, we have a active source, maybe like hammering down the ground, and geophone records the vibration and wave propagates through the media. So in this case, because we generate the source by using some external energy, this is active system. And ground penetrating radar, high resolution near surface seismic method, ultrasonic test of concrete and steel structure is another example. What about passive system? It vibrates by itself, and we listen how they vibrate, right? So then that's passive system. Stethoscope for heartbeat, or electrocardiogram for kidney, and accelerometer to assess the acceleration of moving body. For example, you have a machine with motor inside, and you just hear how they vibrate. Then system itself, it kind of acts itself, and you're just collecting the vibration noise using the accelerometer without any external source of energy. Feedback and self-calibration system. So this is the case that when you consider and improve your system using the output signal. So here the feedback loop is like a trial and error process. And for example, management of the dam and reservoir. So you look at the displacement or deformation of the dam to manage the dam system, or you look at the water level to control the water gate. So you can open the gate and close the gate to control the water level and manage the water reservoir system. Artificial intelligence traffic signal too. Stress anisotropy. This is an interesting example of the soil. And these are the S-wave signal. S-wave signal during loading and during unloading. And in the initial, S-wave signal is here. And as soon as you apply 78 kilopascal, the arrival time gets faster, and it increases with increasing effective stress. And when you unload it from 779 kilopascal, still it's in here, so it doesn't go back to the original position. So it was about 0.0002, and still it's much faster than the previous loading cycle. This is called the stress anisotropy. So the soil is now experiencing anisotropy because of the stress path, the loading and unloading path. So then the system will be the soil, and the input will be the excitation, and the result will be arrival time, or the S-wave velocity. Okay, the next topic is the signal processing. And signal processing is physical processing to understand and analyze the relationship of the energy and frequency or signal which change with time. You can categorize the processing technique into two. One is the time domain method, and the other is the frequency domain method. So time domain method is that when you have a signal that varies with time, you filter or the conditions the signal at the time domain. And frequency domain requires the fast Fourier transform, so you convert the time varying signal into frequency domain, and then do some tricks to get the signal that you want, to remove the noise in general. And noise is defined as all other signals which are not wanted. So that signal processing, purpose of the signal processing is to remove the noise. And digital image processing is the signal processing for advanced visualization, like tomography. Inverse problems. One example, there was a system identification, and the other one is a deconvolution. Deconvolution is to find out the input signal by inverse analysis using the measured output and known system. For example, here, source characterization from remote measurements, environmental monitoring, or detection of the gravity anomaly from surface measurements, forensic engineering, gunman location from sound recording in newscasts. System identification is to determine the system parameter using known input signal and measured output signal. That's like Or in our Earth science, from the earthquake data, we know the input and the output, and then we identify the Earth's mantle structure, how the inner core are made of, and the outer core made of, and the mantle made of. So in summary, signal characterization, decoding, and interpretations are important components of engineering practice and research. And in this class, we talked about the perspectives, engineering perspectives of system. So if there's a system that you can identify, then there must be an input, and then there must be an output. So input, system, output. And depending on what you know, the problem can be inverse problem or forward problem. Revolution in computer technology and digital electronics has led to the development of devices and procedures that operate on discrete signals to the solution of forward and inverse problems that are stated in discrete form. Today's discrete signal processing and inverse problem solving technique impacts all aspects of daily life with countless examples. So then you guys can imagine what will be the future of our geotech and civil and environmental engineering. So this is the end of lecture 1. Thank you for your listening.